In today's lecture, we are going to see the effect of centrifugal force on the value of acceleration due to gravity g. You can also say that we will see the effect of rotation of the earth on the value of acceleration due to gravity g. I hope you all know about the acceleration due to gravity. This is actually acceleration produced by the force of gravity exerted by the earth on any body or any particle. And definitely you have learnt several things regarding this acceleration due to gravity in your lower classes. Okay. In fact, this acceleration due to gravity, which is taken on average 9.8 to 1 meter per second square in general calculation. But you can see that this is not the exact value of acceleration due to gravity at all places on the surface of the earth, but it is just an average value which we take in our general calculation. But there are several factors which affect the value of acceleration due to gravity. Like this acceleration due to gravity decreases when you move in upward direction from the surface of the earth. It also decreases when we go into the interior of the earth. And finally, you can see that the value of this acceleration due to gravity at the center of earth becomes zero. Okay. But here we will see among these factors one of the factors affecting the value of g, and that is the rotation of the earth. Actually, the shape of the earth also affects the value of g. If the earth will not rotate, or you can assume that earth is a non-rotating object, even after that the value of g will be not same on the surface of the earth, because our earth is not a perfect sphere, but it is something flattened at its two poles. So it is just like an ellipsoid. And that's why the acceleration due to gravity, even when the earth will not rotate, will be highest at the poles of the earth, and this will be in fact smallest at the equatorial plane or at the equator of the earth. Okay. But here we are going to consider earth as a spherical body, a spherical rotating body. Actually, you know that the equatorial diameter of the earth is almost 52 kilometer greater than its polar diameter. But in this calculation, we will assume that earth is a perfect sphere having a radius r, which is almost 6400 kilometer. Okay. So taking the earth as a sphere rotating from west to east with a constant angular velocity, we will see what will be actually the effect of this rotation of the earth on the value of g. Okay. You will see that actually this effect is different at different places on the surface of the earth, because this will depend on the latitude of the place where you are considering the value of g. And for this you will have to look back, which we have learnt in the previous lectures, for finding the acceleration of a body in a rotatory frame. I hope you have definitely the expression for acceleration of a body in a rotatory frame. And you can see I have written here that expression directly, that the acceleration of a particle or a body in a rotating frame is given by this expression. This is a dashed equal to a minus 2 omega cross v dashed minus omega cross r minus d omega by dt cross r. Here actually in this expression you know well because you have learnt it in the previous lecture, that this A represents the acceleration of the particle with respect to the inertial frame, and this A dashed represents the acceleration of the particle with respect to the rotating frame. Okay, and V dashed, this is actually velocity of the particle in the rotating frame, or in other words you can say this is velocity of our particle with respect to the rotating frame. Okay, and omega, this is just angular velocity of the rotating frame, and r is the position vector of our particle. Okay, and you know well this expression because you have derived this result and discussed this result in very detail in your previous lecture. Okay, now here we will consider two conditions. First of all, let us see what will happen to this Coriolis acceleration minus 2 omega cross v dashed when our particle is stationary in the rotating frame. It means the particle is rotating with the frame. It has no relative velocity between it has no relative velocity with respect to the rotating frame. So if our particle under consideration is at rest, it is stationary in the rotating frame, then you can simply say that this v dashed will be 0, because v dashed is the velocity of the particle with respect to the rotating frame. But here we are considering that our particle is at rest in the rotating frame, so this v dashed will be 0. And if v dashed will be 0, you can see this term minus 2 omega cross v dashed, which actually represents the Coriolis acceleration, that will vanish, that will be 0. Okay, so you can see I have written here that the Coriolis acceleration in this condition will be minus 2 omega cross v dashed, and that will be 0 because v dashed is 0. Okay, now we consider that our rotating frame is rotating with constant angular velocity. It means omega is not time dependent, but it is constant. And you know, if omega will be constant, then its time derivative d omega by dt will be 0. Okay, and if d omega by dt is 0, this term of acceleration, that is minus d omega by dt cross r, that will be simply 0. So in such a situation, when you consider a particle at rest in a rotating frame and the frame is moving with rotating with constant angular velocity, in that condition these two terms in the RHS of equation 1 become 0, and so then the acceleration of our particle with respect to the rotating frame A dashed will be equal to what? Sorry, this term d omega by dt, this will be 0, and this minus 2 omega cross v dashed will be 0. Okay, so the acceleration of the particle in the rotating frame then will be simply equal to A dashed equal to this much. This is A minus omega cross r. Okay, actually this will be observed when you talk about the effect of rotation of the earth on the acceleration due to gravity. And for this, let us see how the value of g, not only the magnitude of g but also its direction, will affected due to the rotation of the earth. And for this, let us consider this sphere represents our earth. As I have told you earlier, that in this calculation we are considering that our earth is a perfect sphere having a radius r, which is equal to 6400 kilometer. Okay, so this sphere represents the earth. O is the center of our earth, and you know this line which runs from east to west, this represents the equator of the earth, and this N is the north pole and S is the south pole. of the earth, and the line joining this north and south pole, this is actually called the polar axis. Okay, and our earth actually rotates about this polar axis from west to east very slowly with a constant angular velocity omega. So you can say that earth is a rotating frame which rotates with constant angular velocity. Okay, now we consider there is a particle of mass m lying on the surface of the earth at this point P. Mark it. The particle is not moving on the surface of the earth, but it is attached to the surface of the earth. So you can say that the velocity of the particle with respect to the earth is zero. Okay, the velocity v dash of the particle with respect to our rotating frame, which is in this case earth, that is zero. Actually we assume a reference frame attached to this rotating earth, and in that frame our particle is stationary as I have assumed. Okay, actually when you will join this point P to the center of the earth, you can see I have joined this point P with center O, then this line OP makes an angle lambda. This angle is actually lambda here, I have marked it. This angle lambda is subtended by the position vector of the particle with the equator. And you know the angle made by the position vector of a place with the equator of the earth, that is called latitude of the place. So you can say that this lambda is what? This is latitude of the point P or place P. This is latitude. Okay. Now earth is rotating with angular velocity omega about this polar axis, or you can say y-axis. Actually I have assumed here this polar axis as y-axis and x-axis is taken along the equator. Okay. Now since we assume that our particle is rigidly fixed to the surface of the earth, it does not slide or it does not move on the surface of the earth. So it will rotate with the earth. And you know, whenever a rigid body rotates, each of the particle of the body describes a circle. Okay, and the center of those circles lie on the axis of rotation of the body. So you can see here that this particle P will rotate along a circle which I have marked by these dashed lines. These dashed lines represent a circle along which our particle is rotating along with the earth. And this point C shown in this figure is the center of this circle along which our particle is rotating with the same angular velocity. It is also a fact that the angular velocity of the particle will be same as that of the rotating body. Okay, and this CP marked by R in this figure, this is actually the radius of the circle along which our particle is rotating. Okay, so you know in this condition the particle in the rotating frame will experience two acceleration. One acceleration will be the actual acceleration in the inertial frame. It means when the earth is not rotating, then we consider that the acceleration of the particle is A, which will be equal to g, which is actually the actual value or the real value of acceleration due to gravity, or you can say this is acceleration due to gravity when the earth is not rotating. Okay, actual value. But since earth is rotating, so definitely the observed value of g or acceleration will be different. We consider that in the rotating frame of the earth, the acceleration due to gravity is a dashed, which we will represent by g dashed, and this is called actually the apparent value of g. This is called apparent value. In this figure I have not shown this g dashed. We will see what is its direction later on. Okay. And apart from that, since the particle is rotating along a circle, so definitely it will experience a centrifugal acceleration which is away from the center of the earth, center of the circle. So along this direction Cp, the particle experiences centrifugal acceleration, and that is equal to what? You know, that is simply minus omega cross r. And you will see that when we will simplify it, this result will be simply omega square r. We will see later on. Okay. So now in the expression for acceleration of a particle rotating in a rotating frame which rotates with constant angular velocity, and the particle is stationary in that frame, which I have mentioned in this equation 2. Now this expression can be applied for the acceleration due to gravity. Here at the place of a dashed we will write g dashed, which is called apparent acceleration due to gravity, that is the acceleration due to gravity observed in the rotating frame. And at the place of a we will write g, which is the acceleration with respect to the inertial frame. Here that will be called the actual value of g when the earth is supposed to be non-rotating, not rotating. So a will be replaced by g. And so you can see that in this condition g at the place of g a dashed I have written g dashed, at the place of a I have written g, and this term minus omega cross r is at each. Okay. Now see the figure. Actually I have assumed this equatorial line as x-axis and this polar line as y-axis, and this acceleration due to gravity, you know, this is directed toward the center of the earth because our earth attracts the particle towards its center. So g is actually lying along PO. Okay, and in PO you can see that this g vector is in third quadrant, so its both components will be negative. Now in terms of the components of g, how you can write this vector g? You know, g can be written as gxi plus gyj. Here gx and gy are actually the x and y components of this vector g. But from figure you can see, since this angle is lambda, which is latitude of the place P, okay, this is place P, and if this angle is lambda, then you can see that I have marked that this angle will be also lambda. And as the vector lies in third quadrant, so both of its components will be negative. So what will be those components? Actually gx will be minus g cos lambda and gy will be minus g sin lambda. Okay. So in this way we have expressed the g in terms of its rectangular components, that is x component and y component. Now you can see our earth is rotating about its polar axis with angular velocity omega. So this vector omega, in accordance with our supposition, this will be along the y-axis. Okay, and along the y-axis you consider the unit vector j, so omega can be written as omega j. Okay. Now see the position vector r. This Cp is r, which is along the x-axis. Okay, this is actually parallel to x-axis. So r vector can be written as ri, because I is the unit vector along x-axis. Now let us substitute all these values in this equation 3. So you can see that g dash will be equal to what? G, at the place of g we can write g times cos lambda I plus sin lambda j, and minus omega cross r. But omega, you know, this is omega j. Again omega has been written as omega j and r has been written as ri. But you know that j cross I, you know what is j cross I? This is simply minus k hat. Okay. So taking this minus sign here, this minus in our expression becomes plus. You can see it here. And there will be omega rk. But j cross k, you know, j cross k is equal to I. Okay. This is equal to I. So this term has been replaced by omega square r I. So finally we get g dash equal to minus g cos lambda I plus sin lambda j plus omega square r I. Now see this figure. Actually you can see that this is our figure here. In this figure, the triangle OCP, and this angle is lambda, and so in the triangle OCP, since this angle was lambda, so from elementary geometry you know this angle will be also lambda. This is alternate angle and this is your r. Okay. Now here this OP is equal to capital R, which is actually the radius of the earth. So if your aim is to express the value of this small r in terms of the radius of the earth, you can easily see that we will find cos lambda. And from this figure you can say cos lambda will be equal to a small r over capital R, and therefore this small r will be r cos lambda. Okay. So in this expression, this small r has been replaced by r cos lambda here, you can see. Okay. Now we arrange the terms in the RHS. Since here there is unit vector I and in this first term there is also unit vector I. So combine these two terms and let us take minus as a common factor. So this will be simply g cos lambda minus omega square r cos lambda I plus g sin lambda j. Minus has been taken as a common factor. Now you know, if now we want to find the modulus of this apparent value of g, that is mod g dashed, what will be the result? This will be simply a square root of g cos lambda minus omega square r cos lambda whole square and plus g square sin square lambda. Because you know, if a vector is a is equal to axi plus ayj, then what is mod of a? You know, mod of a is simply equal to ax square plus ay square and whole to the power half. Okay. Here at the place of ax there is g cos lambda minus omega square r cos lambda, and at the place of ay there is g sin lambda. Okay. Now the first term g cos lambda minus omega square r cos lambda whole square, this will be simplified on the basis of the formula a minus b whole square. So the first term will be g square cos square lambda. So associate the first term g square cos square lambda with this term g square sin square lambda. So g square can be taken as a common factor and this will be cos square lambda plus sin square lambda. Then the second term will be 2ab. Here a is g cos lambda and b is, second term will be minus 2ab, not 2ab. And b is omega square r cos lambda. So the second term will be 2 omega square r g into cos square lambda. And then you write b square. At the place of b square we will write omega 4, not omega square, omega 4 r square cos square lambda. Here there is actually omega to the power 4, not 2, because already omega contains a power 2, so this will be omega 4. Okay. Now you know cos square lambda plus sin square lambda, that is equal to 1. Okay. And we will also see that this omega, which represents the angular velocity of the earth, this is actually very small. Do you know what is its value? You know that the earth rotates about its polar axis, and the time taken in one rotation of the earth is 24 hours. So you can say that the time period of the rotational motion of the earth is 24 hours. So what will be this omega? You know omega is 2 pi by t, and t is 24 hours. So this 24 will be, when multiplied by 60, it will be in minute. And when you will multiply it by 60, that will be in second. So this omega will be equal to 2 pi divided by 24 into 60 into 60. And when you will simplify it, you will get that this is equal to 7.3 into 10 to the power minus 5 radian per second. Actually, the exact figure is 7.29 into 10 to the power minus 5, which can be roughly written as 7.3. This will be actually easier to remember, and you must remember this value. This value must be in your mind always, because this calculation is not needed to do always. You have to remember it. So you can see omega is of the order of 10 to the power minus 5. So this is a very small number. And when you will put a power 4 on this omega, then this will be of the order of what? This will be of the order of 10 to the power minus 20, of this order. And this is a very small number. So actually the term containing the omega 4, that can be neglected in comparison to the remaining terms. So I have actually neglected this term, and after neglecting the term containing omega to the power 4, your result is what? You can see our result is g square minus 2g omega square r cos square lambda to the power half. Okay. Now let us take this g square as a common factor. But since g square is inside the square root, so when you will take it outside of the square root, then that will be simply g. And inside the bracket, the terms remain will what? At the place of g square, there will be 1. And since in the second term there is only g, but you have taken g square as a common factor, so you must divide this second term by g. So our result is g times 1 minus 2 omega square r by g cos square lambda to the power half. Okay. Now again you know that this omega is very small, so definitely we can think that this omega square r over g times cos square lambda, this will be much greater than 1. Much greater than 1. And you know from binomial expansion that 1 minus x to the power n, this is almost equal to 1 minus nx. But when it is possible, when x is much smaller than 1. Actually this condition, x is much smaller than 1, is satisfied here. At the place of x, you can see there is 2 omega square over g cos square lambda. So applying this approximation, this is actually called first approximation, first binomial approximation. So applying this, our result will be what? at the place of n, you can see here there is 1 by 2. So this will be g times 1 minus 1 by 2 times this much. 2 and 2 will cancel out. So I have written here this is g times 1 minus omega square r over g into cos square lambda. Now let us multiply by this factor g. So your result is g dashed equal to g minus omega square r cos square lambda. This is actually the apparent value of g at a place whose latitude is lambda. Okay, and you can easily see that this second term will be always greater or equal to 0. It is never negative. So in general, we simply say that this g dashed will be less or equal to g. And so the value observed will be not same as that of the actual value of g. In other words, you can say that acceleration due to gravity decreases due to the rotation of the earth. Why due to rotation? You can see if we take that omega is equal to 0, omega is 0, it means you are considering that earth is not rotating. Then what will happen? When omega will be 0, then this g dashed will be equal to g. It means there will be no change in the value of g if the earth is not rotating and earth is also spherical. Then at all places on the surface of the earth, the value of g will be same. Okay, because when you take omega equal to 0, the second term will vanish and g dashed will be simply equal to g. And if the earth is spherical, then the value of g in case of non-rotating earth will be same at all places. Although earth is not spherical, so due to the shape of the earth, g also varies in actual practice. Okay. Now, in this expression, omega square r comes in our calculation, and omega and r both are universal constant. Omega is the angular velocity of the earth, which is 7.3 into 10 to the power minus 5 radian per second, and r is the radius of the earth, which is 6400 kilometer. So for solving numerical problems and dealing the theory easily, you must remember what will be the value of this omega square r. Actually, this omega square r, when calculated, will be found to be 3.4 into 10 to the power minus 2 meter per second square. Because omega, you know, this is 7.3 into 10 to the power minus 5, and radius is 6400 kilometers. So when you will change it in meter, this will be 6.4 into 10 to the power 6 meter. Okay. So after simplification, we get that this term omega square r is simply 3.4 into 10 to the power minus 2 meter per second square. You should remember it. Okay. Now, as you have seen that g dashed is affected by omega, okay, which is angular velocity of the earth, and therefore we simply say that this variation in the value of g is due to the rotation of the earth or due to the centrifugal force acting on our particle. Okay. But you can see that this g dashed also depends on lambda, which is the latitude of the place. And at different places on the surface of the earth, lambda will have different value. And corresponding to that different value of lambda, this g dashed will have different value on the surface of the earth, even when you assume that the earth is spherical. Okay. So now let us consider two standard positions on the surface of the earth. First one I have considered here, the equator. You know, at the equator, latitude is 0. And if latitude is 0, then cos lambda will be equal to 1 and cos square lambda will be also 1. And so, and you know, the maximum value of cos square lambda that is equal to 1. So in this case, we will subtract the maximum value of this factor omega square r cos square lambda from g. And if you will subtract maximum value of this second factor from g, you will get the minimum value of g dashed. So you can say that at the equator, the acceleration due to gravity is minimum. At the surface of the earth, the lowest value or the smallest value of acceleration due to gravity is where? It is at equator. So I have written here that g dashed is equal to ge, which is g minimum, and that will be equal to what? We will take simply cos square lambda equal to 1. That will be g minus omega square r. Okay? G minus omega square r. And you have seen that actually omega square r is equal to 3.4 into 10 to the power minus 2 meter per second square. So from this result, you can see that if we will take the difference of the value of the actual value of g and the apparent value of g, it means actual value of g minus apparent value of g, that will be equal to 3.4 into 10 to the power minus 2 meter per second square. This is actually the maximum difference because g is minimum at the equator, so this is the maximum difference. And this difference is not very large, so in practice we assume that g is almost constant. Although in scientific calculation, you know, this value cannot be neglected. So you can easily see that the difference in the actual value of g and the apparent value of g at the equator is 3.4 into 10 to the power minus 2 meter per second square. Okay, I think you are getting the things. This is a very simple concept. So see the video seriously, everything will be clear to you. Now we will consider that our particle is located at the poles. It means you are considering now what will be the value of g dashed when our point is lying at the poles. You know, at the poles, lambda is 90 degree. Latitude of poles are 90 degree. And cos 90 is 0. So cos square lambda will be also 0. And this is actually the minimum value of cos square lambda. Mark it. Cos lambda's minimum value, cos lambda minimum is not 0. It is minus 1. But cos square lambda's minimum value is 0. Because you know, minimum value of any perfect square is always 0. And so in this case, we will subtract minimum value of this factor from g. And so we will get the maximum value of apparent g. In other words, you can say that this g dashed at the pole, which I have represented by gp, is maximum. And that maximum value is simply equal to the actual value of g. So this is a very remarkable fact that the acceleration due to gravity is not affected by the rotation of the earth at the poles. It means earth is either rotating or non-rotating. The acceleration due to gravity at the poles will be same. It is not affected by the rotation. And so as a whole, you can say that these are poles where the acceleration due to gravity is highest, maximum. Okay? These are very important facts. If anybody asks to you that on the surface of the earth where acceleration due to gravity is maximum, you must say that these are poles where the acceleration due to gravity is maximum. And at the same time, you must state that acceleration due to gravity g at the poles is unaffected of rotation of the earth. It means when the earth will rotate or not rotate, in both cases acceleration due to gravity at the poles will be same. Okay, these are very remarkable facts. But as I have told you earlier, that in our calculation we have assumed that our earth is spherical, but this is not a physical reality. Earth is not spherical, but earth is flattened somewhat at its both poles, that is north pole and south pole. So actually the equatorial diameter of the earth is actually greater than its polar diameter almost by 52 kilometer. So even after the earth will not rotate, the acceleration due to gravity on the surface of the earth at all places will be not same. You can see it here that I have marked here that the actual shape of the earth. And when you consider the value of acceleration due to gravity when the earth does not rotate, neglecting the rotation of the earth, then at the equatorial point, acceleration due to gravity GE will be gm by re square, and at the poles this will be gm by rp square. But re is not equal to rp, re is actually greater than rp, so you can see that ge will be smaller than gp. Okay, these results have been actually written when earth is supposed to be at rest, it is not rotating, then these expressions for g will valid. Okay, that's why actually the earth is not spherical, but we have assumed in our calculation that earth is spherical. So when in experiment you will observe the value of acceleration due to gravity, that will be not equal to that will not differ from its actual value by 3.4 into 10 to the power minus 2 meter per second square. But it is found that the observed value of the difference of acceleration due to gravity at the pole and at the equator is not 3.4 into 10 to the power 2 meter per second square, but it is found that it is 5.2 into 10 to the power minus 2 meter per second square. And why this difference is observed? This is due to the shape of the earth. Due to rotation of the earth, acceleration due to gravity increases by this much. Okay, changes by this much. But due to the shape of the earth, there is an extra change in the value of g. So I have mentioned it here. You can see that this is due to the fact that earth is flattened at the poles. Even if it were not rotating, the values of g at the poles would have been greater than that of the equator. Okay, and the effect of rotation is only to increase the difference by this much. Okay, so observed difference between the value of g at the equator and at the pole is not 3.4 into 10 to the power minus 2 meter per second square, but that is actually 5.2 into 10 to the power minus 2 meter per second square. Okay, so these were the facts regarding the value, that is the magnitude of the acceleration due to gravity, how it varies place to place at the surface of the earth, and this variation is due to the rotation of the earth. But you should be amazed that actually not only the magnitude of acceleration due to gravity changes due to the rotation of the earth, but actually the direction of the observed acceleration due to gravity or apparent acceleration due to gravity is also not same as that of the actual acceleration due to gravity. It means you can say that this g prime is not parallel to g. G prime is deviated by some angle with g. So now we will talk about the direction of acceleration due to gravity. Okay, how the direction is affected, now we will see. Now see, you have actually learnt earlier, you can see it here, that this is the expression. actually I have written here that g dashed is equal to this much plus this much. See this equation. Actually, this is at the place of g. This has been written at the place of g. And this omega square r cos lambda I. This is actually the centrifugal acceleration. So this g dashed is equal to the actual value of g plus centrifugal acceleration. Okay. So, and this fact I have shown in this figure, you can see. The actual acceleration due to gravity is directed along this direction PO, that is in vertically downward direction toward the center of the earth. This is actually our earth and O is its center. Okay. And omega square r cos lambda I, this is your centrifugal acceleration, and you know this is directed away from the center of the circle described by this particle. Okay. And since g dashed is equal to g plus omega square r cos lambda I, as we have seen earlier. So according to triangle law of addition, definitely this g dashed will be directed along this direction PO dashed, deviated from the direction g by an angle alpha, as I have assumed. You can see that this equation which I have mentioned it here, that g dashed equal to g plus omega square r cos lambda I, is just satisfied considering this triangle POO dashed. Okay. So you can see that the direction of g dashed makes an angle alpha with this g. Actually this alpha is very small. So in practice this is not always considered, but in scientific calculation we must know that by what angle the direction of g dash deviates from the direction of actual g. Okay. And you can see this we know the value of g, g dashed and omega square r cos lambda, and we have to actually obtain the value of this alpha, that will be the measure of direction of g dashed. And this alpha can be easily calculated by using the properties of a triangle. When you study properties of a triangle in your course on trigonometry, there you actually see a formula which is called sine rule. According to sine rule, when we will divide sine alpha by the side of the triangle in front of it, that will be equal to sine lambda divided by the side PO dashed. So utilizing the sine rule, you can write sine alpha divided by omega square r cos lambda equal to sine lambda divided by g prime. But we have to find lambda, so must write sine alpha equal to what? This is omega square r sine lambda cos lambda over g dashed. Now let us multiply by 2 in the numerator and denominator. So I have multiplied by 2 here, you can see. But you know 2 sine lambda into cos lambda, that is sine 2 lambda. So instead of that I have written here sine 2 lambda, and the remaining factors are omega square r over 2g dashed. But as I have told you that this alpha is very small, and later on we will find the value of alpha, and then you will see that it is actually very small. And you know, when an angle alpha is very small, in that condition sine alpha is simply equal to alpha, because you have learnt in your calculus in the chapter limit that limit alpha tending towards 0, sine alpha is equal to alpha. Okay. So instead of sine alpha, I have written here alpha. So alpha is omega square r divided by 2g prime sine 2 lambda. This is the expression for alpha. So you can see that the direction of the apparent value of g, that is g dashed, makes an angle alpha to the true direction of the acceleration due to gravity, and that alpha is equal to this much. And that's why we simply say that when you suspend a plumb line, you suspend a plumb line, then this plumb line actually does not point to the true vertical direction, because this will be along the direction of g dash, and g dash is not in the truly vertical direction. So a plumb line is always deviated by some angle from the true vertical direction. Okay. Now, what will be actually the value of this alpha, or you can say of what order its value, you can check it. Now, again, this omega square r over 2g dashed is over g dashed is a universal constant, and so we can write it here omega square r by g dashed. As you have seen that g and g dashed, g minus g dashed, this is only 3.2 or what? 3.4, not 2. This is only 3.4 into 10 to the power minus 2 meter per second square. This is the difference of g and g dash. This is a very small difference, so we take g dash also almost equal to g, and so I have substituted here at the place of g dash 9.8 meter per second square, and omega square r, you have seen this is 3.4 into 10 to the power minus 2 meter per second square. And when you will simplify it, you will get that this is almost 1 over 291. So remember this value. This value is also very useful in solving the numerical problem. So you must remember it. Okay. Now you can see that the value of alpha 2 depends on the latitude of the place. So now let us test what will be the value of alpha when we will talk about some standard position on the surface of the earth. And you know, we always take two standard positions. First one is the pole and the another is equator. So when you will consider that our point is at the pole, then lambda will be 90 degree. And you know, if lambda is 90 degree, then what will be this sine 2 lambda? This will be sine 180, and that will be 0. And so sine 2 lambda in this case will be 0, so alpha will be 0. This is a very interesting result. You can see that actually at the poles, the actual acceleration due to gravity g and the apparent acceleration due to gravity g will be in same direction. There will be no deviation of the plumb line when it is suspended at the poles. Okay. This is a very remarkable fact. Now we talk about equator. You know, at equator lambda is 0, and so sine 2 lambda means sine 0, and that is also 0. So in this case too, alpha is also 0. This is a very remarkable fact. Magnitude of acceleration due to gravity are not same at the equator and at the poles, but they differ by the largest difference. The value of g at poles is highest and that at equator is lowest, but direction of g at the poles and at the equator both are in the direction of the actual acceleration due to gravity. So when a plumb line will be suspended above the equator, then it will point in the true direction of acceleration due to gravity, or it will point in the true vertical direction. Okay. So there is no deviation of g with its actual value, with its actual direction at the poles and at the equator too. This is a very significant point for objective question, because common people will think that the direction, the deviation, if it is 0 at poles, then it will be not 0 at equator, but at both places these are equal to 0. Now consider a place where lambda is 45 degree. If lambda is 45 degree, then you know sine 2 lambda will be sine 90 degree, which is 1, and that will be the maximum value of sine 2 lambda. And you can see when you will substitute maximum value of this sine 2 lambda, alpha will have a maximum value. So you can say that the deviation of acceleration due to gravity from the true vertical direction is maximum if we talk about a point at a latitude 45 degree, or you can say that a plumb line will suffer maximum deviation from the true vertical direction when it will be suspended at a place whose latitude is 45 degree. Okay, but what will be that value? You can easily find. For this we will simply substitute sine 2 lambda equal to 1 in this equation B. So alpha at this place will be simply omega square r by 2g prime, but omega square r by g prime is 1 by 1 by 291. So alpha will have a maximum value. Sorry, the page has been turned, but this will be just okay. Let us see. So this will be equal to what? This will be 1 by 2 into 1 by 291. And when you will simplify it, this will be simply 1.7 into 10 to the power minus 3 radian. And this value in degree is 1 by 10 degree, or in minute it is 6 minutes. You can see how smaller is the maximum value of this alpha. This is maximum value. In general, alpha will be smaller than this. So the highest deviation of the plumb line from the true vertical direction will be only of 1 by 10 degree, that is 0.1 degree. So you can think that in practice such a small deviation is neglected, and we consider that the acceleration due to gravity g dash also points in the true vertical direction. Okay, but you know, in scientific calculation this value of 0.1 degree is also significant, because whenever you make a scientific calculation, then even the nano degree, nano degree, pico degree, atto degree, that is also important. Okay, so in practice this is not very significant, but in scientific calculation you must take it into account, and you should say that the plumb line suspended at a place on the surface of the earth actually does not point to the actual vertical direction or true vertical direction. So I have mentioned it here, you can see, hence a plumb line at P will not point in the true vertical direction PO, but along PO dashed, which is displaced from the vertical by a small angle equal to 6 minutes. So I think after watching this video, your concept regarding the effect of rotation of the earth on the magnitude of acceleration due to gravity and direction of acceleration due to gravity have been definitely clear to you. Okay, thank you very much.